Okay, I want to give a quick run through here of some unusual molecules and how you figure out whether those molecules are polar using these unusual molecules. I want to use this strange formula here. This is carbon and sulfur and 2 bromines. So notice that you have to have capital letters as the first letter in an element symbol, or you won't know that it's the right symbol. If I didn't have capital C and capital S, I wouldn't know that's carbon and sulfur. Capital C and a small s would be cesium. So you have to be careful about the correct capitalization in small letters to indicate what actual element you're looking at. We're going to combine those together into a molecule. And so what I want to do, this is the electron dot formulas, or these are the electron dot formulas for these 4 atoms. And I want to arrange these in a way where all these atoms can have 8 electrons. All of these atoms are past the first primary energy level. They're down in this section here, so they want to be like the noble gases at the end of their row. Carbon wants to be like neon, sulfur wants to be like argon, bromine wants to be like krypton. They all have 8 electrons. That is the noble gases, the elements on the far right over here are noble gases. They have 8 valence electrons. So all of these other elements want to be like that, in that they want to have 8 valence electrons when they're doing this covalent bonding. So to get sulfur up to 8 electrons from its 6, I can share an electron with carbon here and a second electron with carbon. Okay, and that brings sulfur up to 8. Carbon is currently at 6, but if I share 1 each with bromine, bromine has 7 electrons, needs 1 more. So that gives this bromine 8, and this would give this bromine 8, and it also gives that carbon the 8 electrons it wants. So by doing that, then, all of these have a noble gas electron configuration through sharing of electrons, and sharing of electrons is covalent bonding. The way we show that with the Lewis dot formula is if we share 2 electrons like this, they're squeezed together, they look like that. If I share 2 electrons between this carbon and this bromine, they look like that. Here between carbon and sulfur, I'm sharing 4. We put that in a kind of like 4 corners of a box or something. And then we need to put the lone pairs. The electrons that remain on the outside, those also need to be on here for the Lewis dot formula. And sulfur has 2 lone pairs out here. Okay? So that's the Lewis dot formula. What we want to do is take a look at that Lewis dot formula and figure out how many sets of electrons there are between the atoms in this formula. So shared between the atoms of bromine and carbon, there is 1 set, 2 electrons, but 1 set. All the electrons shared between bromine and carbon make up a set. So there's 1 set here. All the electrons between this carbon and this sulfur, there's 4 electrons, but it's still 1 set because all the electrons between carbon and sulfur make up a set. It's also true that around the atom of interest, if there are any lone pairs, there aren't any here, but if there were lone pairs, that also makes up a set. But since I have 3 sets around that carbon, I want to arrange those as far apart as I can get them in 3-dimensional space, and that's 120 degrees around or between each angle from the carbon atom to the other atom, or to the set of electrons. What we're first going to do is what's called an electron pair shape. We're going to put the sets of electrons on the ends of these arms, and this set up here above the carbon, that's 4, so we want 4 electrons there. It really doesn't matter which arm you put the double set on, the 4 electrons. They could be down here or over here. It doesn't really matter because these are all evenly spaced. There's no preference for putting that double bond. That's what it's called. Sharing 4 electrons is a double bond. There's no preference for putting on any one of the arms. So I just did it this way for this time. So what I'm going to do, what we want to do next is to replace any shared sets of electrons with the symbol for the atom with which they're shared. So this set of 4 is shared with sulfur. So I want to replace that set with this symbol for sulfur. And these 2 down here are both shared with bromine. Here they're shared with bromine. That's what we made out here and here. So we're going to put bromine down here. Okay? So what we have is a trigonal planar molecule. This is called an electron pair shape. It's also trigonal planar. If we had a stage in between where we had some kind of a drawing that had both atoms on the outside and lone pair somewhere, we'd have what's called a modified electron pair shape. We don't have that today. We went straight from the electron pair shape, which is trigonal planar, to the molecular shape, which is trigonal planar. What I want to do now is find out, well, is this molecule polar? I know that it's symmetrical, three-dimensionally symmetrical. We know that in every direction you go, it's equal, all the bonds are equally spaced, and that's called symmetry. To find out if the bonds are polar, I'm going to look at electronegativity. And for my class anyway, there is a periodic table that I give students, which has all the electronegativities for all the elements listed. It looks like this. And I can see that carbon has an electronegativity of 2.55, sulfur has an electronegativity of 2.58, and bromine has an electronegativity of 2.96. So we need to find out about this bond. This bond is the same, so we only need to know about the bromine to carbon bond. We also need to know separately about the bond between carbon and sulfur. So let's see. Let's look at the bond between bromine and carbon first. So bromine has an electronegativity of 2.96, which is larger than carbon. So we'll put bromine's electronegativity above that of carbon, so that I can subtract and get a whole number. Bromine is 2.96. and carbon is 2.55. Now, what is this electronegativity? This electronegativity is a relative measure, a comparison of how hard atoms pull on electrons they share with another atom. So you can see that bromine, because it's a larger electronegativity, it's pulling on the electrons of carbon more strongly than carbon is pulling on those same electrons that it shares. So these electrons between bromine and carbon, bromine is pulling harder on those electrons. Well, let's find the difference here. So we got 0.41. And that electronegativity, that's the bond between carbon and bromine. That electronegativity is less than 0.5. And different professors, different textbooks, different teachers have a different starting place for polarity. For my class, just to make it easy, I say that 0.5 and above, or actually above 0.5, is polar, would indicate we have a polar bond. Okay, well, this is less than 0.5, so we consider this bond non-polar. Okay, that's like a PDR, but it's supposed to be polar, P-O-L-A-R. I'll fix that when it dries, and we'll put some white out on it and fix that in a minute. Just kind of put the letters too close together. Okay. Now let's look at the bond between carbon and sulfur. So carbon is slightly less electronegativity than sulfur, so sulfur is going to go on the top. 2.58 is the electronegativity for sulfur. 2.55 is the electronegativity for carbon. 0.03 is the electronegativity difference for carbon to sulfur bond. And so this bond is also non-polar. So in this case, all the bonds, even though we have different kinds of bonds here, all the bonds in this molecule are non-polar. And so if they're non-polar, the molecule can't be polar. All right? So we have a symmetrical molecule, but there's different bonds. Since there's different kinds of bonds, we need to look at the electronegativity of each individual kind of bond. But since all these bonds are non-polar, the molecule cannot be polar. You have to have polar bonds to have a polar molecule. But I want to take and switch out bromine with a different element. So both these bromines I'm going to replace with chlorine and see what that does. Okay, so instead of capital C, which is carbon, capital S, which is sulfur, capital B, little r for bromine, that was subscript 2 bromines. I want to use C, S, and chlorine. Bromine and chlorine are both halogens. They're right here in the same row or column, rather, of the periodic table. They're both halogens, okay? But they have a different electronegativity. Notice that chlorine's electronegativity is 3.16. So we're going to go through the same process here. I've pretty much written all this out. All we got to do is calculate the electronegativity. But notice the molecules here look the same. Okay, the difference is that instead of bromines down here, I have bromines down here, I now have chlorines down here. And I could have had the sulfur over here and the chlorine up there. It doesn't matter. We can still get to the same answer. But let's find our electronegativity difference. So the electronegativity for, let's look at the carbon-chlorine bond then. Chlorine has a larger electronegativity. We're going to put it on top. So electronegativity is 3.16. And carbon's electronegativity is 2.55. So that's an electronegativity difference of 0.61. For the chlorine to carbon bond, electronegativity is 0.61. Well, that's clearly polar. That's greater than 0.5, and that's the sort of the rule we use in my class. So this is a polar bond. Further, we can see that chlorine's electronegativity is greater. Okay, so it has a higher electronegativity. We're going to use something that I like to call a dipole arrow to show the direction the polarity goes in terms of which of the two atoms has the greater electronegativity. So what I'm going to do is, since chlorine has a greater electronegativity, the electrons, by definition, electronegativity is how hard an atom pulls on the electrons it shares with another atom. So the electrons in this bond tend to be closer to chlorine most of the time. It's pulling harder on those electrons, keeping the electrons down here more, and so that makes it more electronegative. Okay, so I'm going to have an arrow showing that. Okay. Now the sulfur to carbon bond, we actually already calculated that up here. 2.58 is the electronegativity for sulfur, and carbon is 2.55, and so our electronegativity is 0.03, so that electronegativity between carbon to sulfur is nonpolar. So in this case, I'm not going to show a dipole arrow. But here's the thing, because of these two arrows, because of this one's nonpolar, and these two arrows here, the overall direction of electronegativity is sort of you might say, is flowing out here. So the electrons tend to spend more time out here around the chlorines than they do around the carbon or the sulfur. Okay? So that makes this end of the molecule, this whole end of the molecule down here, more electronegative than this one is. So the overall, for the whole molecule, the dipole moment appears to lie in this direction for the molecule. This is the molecular dipole. These are bond dipoles, or bond dipole arrows. This is a molecular dipole arrow. It shows that the direction of the electronegativity is in this direction. What it also means is that this end of the molecule is partially negative. That's our symbol for partially negative. It's like an 8 that you didn't quite finish, or an S that you sort of looped back on itself. And up here, because this is partially negative, this end up here, by comparison, is partially positive. So this molecule then is a polar molecule, because even though this molecule is symmetrical, the molecule itself is evenly spaced all the way around, the polarity is not equally spaced. The polarity is uneven. It's almost as if we had nothing up here at all in terms of the polarity. Everything's down on this end, making this a polar molecule. So because we have a symmetrical molecule, but an asymmetrical polarity, then this is a polar molecule. Okay? And a polar molecule is a molecule that has a dipole, two poles, 1, 2. So this is a molecular dipole. All right? Our first molecule up here, where we had bromines instead of chlorines, this one is nonpolar. And it's nonpolar because we don't have enough polarity in the bonds to create polarity for the whole molecule. So it's not a dipole. Okay? This one is. So when you're figuring out whether molecules are polar or not, you've got to look at all the bonds and the overall direction of these dipoles. And it's really a matter of just kind of figuring it out. Got to be able to use the old white matter in your brain to try and sort it all out. What does it all mean? Where does everything head to? Where is the greatest amount of electron density? So this end of the molecule here, because the chlorines are pulling electrons to themselves more than carbon or sulfur, the electrons tend to be down here more often, so we call this end of the molecule more dense in electrons. This end of the molecule has a greater electron density. This end of the molecule has a greater electron density than this end, and that makes it a polar molecule. The greater electron density makes this end of the molecule more negative because electrons are negative.